All right, this is the FP1 paper from 2023. Let's just go ahead and do it. Bit of Simpson's rule first. So it says 4 intervals. So we start at 0, end at 2. The 4 intervals between 0 and 2 will be a half, 1, and 1.5, of course. That gives you 4 intervals between these things that you're doing. Then you just input what happens at x equals 0, where sine squared of 0 is just 0, e to the 0 is 1. And likewise for 2, and likewise for all the other ones. Just input the number into here and work out what the y value is. You get all these numbers. Now, Simpson's rule isn't given to you in the formula book, but it is this. This is just what you want to have in your head. It's a half times the h, which is the distance of each interval, so that's a half in this case. The ends are this value and this value. The odds are the first value because the ends don't count, so the first and the third value, so that's going to be this plus this, and the evens would be the second plus the fourth, which doesn't exist again because that's an end value instead. So we end up with this here. So imagine this being the first, the second, and the third. That's an even thing, and these are odds, and then these are the ends at the end there. Good. We just type that in the calculator and we get this. This is close. It's accurate to 2SF, which is apparently all you need to say. So worth bearing in mind. That is all you need to say there. Given t is e to the x, that means dt by dx is also e to the x, which is t. So that's kind of a useful thing to know. dh by dx could be written as dh by dt times dt by dx. By chain rule, you could cancel out these dt's, I guess, and you'd end up with this being true. But dt by dt by dx is known. That's just t. So we end up with the first line they wanted us to get. The second one, likewise, we could start maybe by just differentiating this thing here by product rule. So the derivative of that is the second derivative, leave that alone. And then the derivative of that is, of course, 1 with respect to t, leave that alone. Now, we need to derive this side with respect to t. To do that, we'll just derive this side with respect to x, and then just times it by dx by dt. So this side with differentiated with respect to x is d2h by dx squared, and then just slam a dx by dtx to it, because that's what you actually differentiated with respect to here, and this is what you wanted to. So that's kind of what goes there. But of course, dx by dt we've already seen is 1 over t. You could just flip this whole thing over, and then times everything by t, and you'll end up, I think, with this, if you just take away, what do we have to do here? Oh, sorry, yeah, this thing here is from up here, dh by dx, and then we could take away from both sides, and we'll end up with this line here. I don't think I actually bothered to do that. No, I didn't. Good. Anyway, this one here, so we put this result into here, and we put this result here into here, and I think we just end up with this. So those two terms come from what this one changes into, and this term here comes from what this double thing turns into there. And then, of course, it ends up being very simple. You put it together, and t cubed, of course, is e to the 3x. C to the x cubed, that's e to the 3x. Good, so that's there. Hence, show this thing here. So let's solve the auxiliary quadratic first, m squared minus 3m plus 2. That gives you answers of 1 and 2 if you factorize or use your calculator, it doesn't matter. So you have solutions, it's two distinct reals, right? So it's a e to the first plus b e to the second of x. The next bit, we need to just say maybe x or h, sorry, should be lambda or k e to the 3x, any just constant here. Differentiate this to get k, 3k e to the 3x, I guess. Differentiate again to get 9k e to the 3x, and shove those three results into here to find out what k needs to be. You get k as a half. And then, of course, that means that the full answer is going to be this plus a half e to the 3x, which is basically what they wanted, except e to the 3x going back a step. E to the 3x is t cubed, e to the 2x is t squared, and e to the x is t. So we end up with that there. I think we're all happy with that now. Good. And yeah, now we have some stuff we can put in. So put in 1 and 2.5 into this, and we end up with this. Pretty clearly, you get this, I guess, if you simplify. And then to make this one useful, we're just going to have to differentiate this line here, which gives us dh by dt. It's just a plus 2bt plus 3 over 2t squared. Put in these two values now. Rearrange, maybe, or just write it out twice for no reason, and then maybe use a calculator to solve these two things, or do it on your own if you're feeling ambitious, and you get those two answers there. And yeah, so that would be that answer there, and then determine the height after 5 seconds, where we just put 5 in, and we'll get our answer to this question as well. And we'll move on to question 3. So firstly, the curvy bit with the modulus is this curve, and then this is obviously just this line. So this question is really asking us, when is the curve below the line? So let's just mark our areas. Over here, the curve is below the line. Not here, the curve is above the line here, but in between these two coordinates as well, these two intersections, the curve is also below the line. So the answer will be something x less than something, and over here, x between two things. Now, this asymptote here is clearly x equals -6, because that's when you start dividing by 0, and so the curve goes off to infinity there. So basically, this curve here, we actually don't need the mod sign. This curve here is just the quadratic over x plus 6, because for every value to the right of this asymptote, x is bigger than -6. So therefore, this modulus function isn't doing anything. If x is bigger than -6 in here, you just get a positive number, and the mod function doesn't do anything. So this curve is just this curve here. So we can actually just set that equal to the line, and solve this equation to find our two intersections. So yeah, we'll just times by x plus 6, I guess. We'll expand, we'll rearrange, we'll use a calculator to answer that question for us. And we'll end up with this point being 2 and this point being -27/5. And then likewise over here, this curve is literally just, if x is less than -6, then the mod function, the thing inside the mod function is going to be negative. And so the mod function is going to times the whole thing by -1 to make it positive. So by the way, that's of course half our answer between those 2 points there. That's this half of it. But in this part here, this curve is just this. The mod function is just timesing this by -1 to make it positive. But then we can just solve this equation, right? And we'll end up with this quadratic, which solves to make this, again, using a calculator. And so we, of course, our thing is negative here. It's way over past -6. So we want to do -7 minus root 57, and we want x to be less than that thing there. So those would be our two answers there. And we'll be done with question 3 as well. Look in the table for eccentricity of an ellipse, and you end up with this. Clearly, A needs to be 4, because 4 squared is 16, and B needs to be 3. So we just put those values in there, and we solve 3 very quickly, and we get, because of course E needs to be, I think E is supposed to be a positive value. No, I think that's by default. So sure. Anyway, that's just why I haven't done the minus or the plus minus. I actually forgot at the time I was doing it, but we'll just keep it. The points P and Q are this. L is normal. Okay, so what we need to do here is we need to first differentiate our ellipse, because of course this is about gradients, right? To work out a normal. If you're doing a year 12 A-level maths question, you sort of need to do with the normal to a curve, you would differentiate the curve. So we're just going to differentiate this thing here. Going to use a bit of course, deriving that with respect to x is easy. Deriving that, you just slam a dy by dx on the end, as we saw in that differential equations question. Rearrange that for dy by dx, and you end up with this. And then what you can do is you can throw your x value and your y value into there. This is talking about the point P here. So put that x and that y in there, and that's our gradient at the point P. So now we can simplify it, I guess, a little bit. But now we can say the gradient of the normal is, of course, the negative reciprocal of this, because it's the normal. And then to work out the equation on the line of the normal, we can just do y minus y1 equals m, which is this, x minus x1. And this, if you verify it yourselves, this definitely turns into this, which is what they wanted you to get. The line L2 passes through the origin and point Q. Well, that's actually quite simple. That just means it's this equation. It has a 0 y-intercept, and the gradient is just going to be this over that. So that's easy. So that's just the line L2. Find when they intersect. Well, what we can do here is we can throw this result for y into the one we just got. The causes cancel here, which is nice, and some other stuff happens, and then we can divide everything here by cos theta, I think is what I did at some point. No, sorry, divide everything by sine theta. Sine theta isn't 0 because theta is definitely bigger than 0, so that's fine. And we can solve this for x, it just equals this, and then we can put that value into there. The causes will cancel, and you'll end up with y as this. So that's good. So those are the coordinates. I probably should have put them in a bracket here, but I couldn't be bothered to type it. But the coordinate is this, comma this in brackets. And then hence show that R is an ellipse. So an ellipse obviously has this equation, as we saw earlier. If we just choose A, I mean, x squared is this fraction squared, cos squared theta. If we choose A to also be this fraction squared, then that will just cancel, and you'll end up with cos squared theta. And then if you do the same for y, and you choose this thing to be B, or B squared, to be B, then you'll just get cos squared plus y squared equals 1, and it'll be fine. So you just choose A and B to be those two values. You don't need the negative because it's squaring anyway. And so that's fine. We'll just choose that, and then we can work out the eccentricity using the same formula we saw before by shoving in the A and the B result, and we rearrange for E, and you can do it yourself, but you end up doing some simple maths and getting the same answer that we did before. And that's question 4 done. We're going to do a T substitution here, or a Weierstrass substitution, I think is the other way of naming it. This works because the derivative does something nice. dt equals sec squared x over 2 times a half dx. And then, of course, sec squared is actually just 1 plus tan squared. You can times everything by 2 as well. But, of course, tan squared is just t squared. So you end up saying this is 1 plus t squared, dividing by it, and this ends up being the thing that you put in for the dx. And that happens every single time, which is nice. You also can just memorize, you do not need to derive these, you can just memorize that sine x is going to be, it's 2t over 1 plus t squared, if that's the substitution, and cos x is 1 minus t squared over 1 plus t squared for that substitution. You can throw all of these three things in here to get this. I'm going to combine all of this denominator here together, which ends up being this, times that by 5 into 1 plus t squared over 1 plus t squared to make the denominators match. And then this 1 plus t squared cancels with this one, which is kind of why this t substitution works so much of the time, is because of that cancellation right there. You end up with this, you can divide over by 2, and you end up with that as required. Hence determine this. So obviously this is just this. So we can start there, factor out a third from the denominator, and take that out of the thing, and then you can start computing the square on the denominator as well. And the reason that's helpful is because you now can get it in the form this, and you can look up the integral of that kind of thing. This isn't an x squared, it's a t plus a third squared, but that doesn't make a difference because you can make a substitution back again of just like, you know, u equals t plus a third, and you'll see that the du dt, because it's a linear transformation, doesn't do anything. And you can just essentially, in this case, just pretend that this says t plus a third and this says t plus a third, and it's all just good. Of course, a is root 5 over 3. So 1 over a is 3 over root 5, and likewise over a is 3 over root 5 here. So we end up with this kind of answer. And you can put the t back. T is at tan x over 2, because of course the original integral was in terms of x. And this will be our answer there, which is kind of cool. Question 6 then. So we're going to differentiate this. The differential of a log is just f dashed over f, where the function is the thing inside the log itself. So this is just f, so that goes on the bottom. To differentiate this, just do some product rule. So it ends up being 2e to the 2x times this on its own. And then differentiate this, which makes a minus 3 sine 3x, and you end up with this here. Apparently that needs to be this, where we can cancel all the e to the 2x's, and then we can break the fraction up in half here, and then these cancel, and you just end up with this being a tan, and it ends up being this here, so that's good. To differentiate that again, super simple, it's just going to be minus 9 sec squared, so that's fine. Differentiating this isn't so trivial. We can say sec squared maybe is cos 3x to the power minus 2, and then do some chain rule. That's just how I did it. So minus 2 times minus 9 is 18, but then we also going to have to times by the 3 that's going to come out here to make 54. Lower the power down to minus 3, and then also times by the derivative of this. I actually already did that for one of the 3's, but this also becomes a minus sine 3x. So that's the third one. And then the fourth one, we have to do that kind of thing again with some product rule. So this one here comes from differentiating this one, leaving this one alone. I'll allow you to check that if you want to. The square comes from this, just differentiating to make another copy of this. And then, of course, this one here is from leaving this one alone and differentiating this one here. You end up with this here. So yeah, not too easy, but just some product rule and some chain rule mixed together. Good. First 3 terms of the Maclaurin series. So this is the Maclaurin series here. So we need to work out f of 0, which is just e to the 0 is 1, cos of 0 is 1. So this is just log of 1. F dashed of 0, tan of 0 is 0, so that's just 2. F double dashed of 0 is this. Now cos of 0 is 1, which is just still 1 times minus 9 is minus 9. F dash dashed of 0 is actually 0, because the third derivative, when you put in 0 sine, just makes the whole thing go away. And the fourth derivative, these are just 1, so it just ends up being a minus 162. Good, and then these 2, 6, and 24 come from 2 factorial, 3 factorial, and 4 factorial on the bottom of these things here that would be there. Good, log of 1 is just 0, so this simplifies down to this as well. Good, the Maclaurin series of this, if we just look up in the formula book, is this. If you replace x with a kx, this becomes kx, this becomes kx all squared, which is k squared x squared. This becomes kx all cubed, which is k cubed x cubed, and so on. And you get that. Hence, do this thing here. So these are the 2 results we've got so far. Now, this is log of this thing over this thing. So if we subtract these 2 results, which gives us this minus this by log laws gives us log of this over this. So that becomes that. I've minused these by just combining the x's, the x squareds, and so on to make this. And just be careful of some minuses that happen in here. And now just divide everything by x squared, which makes this, and take the limit as x tends to 0, which will be the limit as x and 0 of all of this here. Now, all of this is fine. Taking the limit of x tends to 0 of all this is of this term is fine because it just goes to 0. This term is fine, it goes to 0. This term is just itself, it doesn't do anything. This term is not fine. If x goes to 0, then this term goes to infinity, but we can fix that by setting k to be 2, and then this term goes away before you start taking the limit, and then everything else will be fine. So k is 2 is the thing for which that limit will actually exist. And the last question is about vectors. This line form here, we're not actually going to use in any way. You probably could use it, but this is just a point that goes through the line, and this is the gradient of the line, so we can just write it as this, I guess, in normal kind of core pure vector form. We can crowd that up to make this instead, and I'll just draw it. This is the line. We've got a point 365, and we want to know that B and C lie on this line, so maybe this is B and this is C, such that the distance is 15 for both. So what should we do? Well, let's work out this vector here, which is just this minus this. You could do. You could also do this minus this. It doesn't really matter. Let's do this minus this to work out this vector to get from here to here or from here to here. It doesn't really matter, of course, which direction you go, as I just said. And now we just want this vector to have distance 15. So we want the square root of this squared plus this squared plus this squared to equal 15. Square both sides and work out all of this expansion, and you ended up with this, and you also move the 225 back over to make it equal 0, of course. You sit here for an hour factorizing this, or you just type it into a calculator and get this. And so if k is either -1 or -2, then we can shove that into the line. So if k is -1, we get 12, -7 is 5, and then 27, and sorry, 17, and so on. So that would be the point B. It could have been this one here. It obviously doesn't matter. And the point C is when k is -2, let's just say, and C will be this here. So that will be our B, and that will be our C. Hence, determine a Cartesian equation of the plane. So the plane containing in it has these 3 points, which means it has this vector and this vector in it. So let's just work out what those 2 vectors are. It's this and this, I guess. So what we can do, if we know the plane has this vector and this vector in it, we can cross these 2 things together to work out a thing that's perpendicular to both of those vectors. And of course, a plane in Cartesian form just has that perpendicular vector as the coefficients of x, y, z, as we've seen in core pure. So let's just cross those together. That just makes this is how I do it using this matrix. It's I times the term of this minus j times the term of this plus k times the term of that. You end up with this. And so we can just use those coefficients in our plane, like so. And then, of course, we need to know what k is. So we just shove in any one of the 3 points. It doesn't matter which one in to find k, and that'll be our equation of the plane. Next, we've got a point D, which is this. So let's just put it up here somewhere. And given the volume of the tetrahedron, so we need a formula here. Firstly, I've worked out this vector is this, just to get you from here to here is just that, right? So the formula for tetrahedron, if you have vectors A, B, and C, is this thing here. Now I can use any of these 3 that I want. I'm imagining the tetrahedron to, of course, be this kind of shape here. I can use any of these 2 vectors that I want as A, B, and C, but it will be easiest, I think, to use this one as A, because then I can cross together the 2 things that are just here, which I've actually already done, which is nice. I've actually already crossed those 2 vectors together in this part here, which is very good. So that's the other reason to use A as the lone one, aside from not having an alpha in a cross product. But we've already crossed those together. That just makes this. And now we dot them together to make this. And we get times everything by 6, we get this. So this means either if the mod doesn't do anything, then this equals 882. Or if this whole thing is negative, then the mod is timesing the whole thing by -1, and minus this equals 882. And either way, you end up solving this for alpha is this, and alpha is that. Now, alpha is bigger than 0, so therefore alpha is 7. And our picture updates itself to this. And L2, I'll just call L2 the line connecting A and D, is just this here. It's just this point plus the amount you need to get from here to here, which is this. So that's L2 in vector form. And a super useful little formula for working out the shortest distance between 2 skewed lines, our lines being this one and this one, is given not in the formula book, it's given in the textbook, but you would have to memorize this formula, so that's worth knowing. Now, there is a completely different core pure method for doing this question, which if you want to see, you can look in the core pure book and watch my core pure videos, and you'll see a method for working out the shortest distance between 2 skew lines without this. But if you do want to just memorize this, kind of useful because of course it's quicker, and because you could use it in core pure exams if you wanted to. There's nothing stopping you from knowing the cross product and using this formula in there. So yeah, this formula is kind of useful. B we'll just use as this vector. D we'll use as this vector. So that's the gradients of each line. And A and C we'll use as this one and this one. And we just plug them in, right? And we've got a bit of work to do here. We've got to cross together these 2 things, so that's the first thing I'll do. It just makes this, do that very quickly. Replace those with both of those, then dot those 2 things and work out the modulus of that vector by doing this. If you dot those, you get this. The modulus here will just change that to a plus, and then of course you can type that in, and we'll end up with 4.4. Thank you so much for watching. Do memorize that formula since it's useful in both FP1 and core pure 1 and 2 if the shortest distance between 2 skew lines comes up. just a much faster way of doing it if you're comfortable with it. I'll see you next time.